Welcome. In this talk, I'm going to describe a new paradigm for modern full-stack web development that is competitive with React.js, GraphQL, and Relay. At Hyperfiddle, we've been researching how functional programming can be applied to simplify web development. This is the result of that research. As a problem statement, this here is the code we as web developers wish we could write. There are client-side DOM effects and server-side queries. It feels like such a composition should be well-defined, but it's not because of how the web works. The network makes us split our composed program into two separate programs, breaking function composition. This is basically an impedance mismatch. Your programming language is designed for single programs, but your application as a whole is a client-server distributed system. This impedance mismatch is the root cause of complexity in web development, and we think functional programming can solve it. At Hyperfiddle, we designed a new programming language called Photon, which is hosted by Clojure. Here you can see in Photon we mark the client bits and the server bits. pdefin, which defines a Photon function, is a Clojure macro. It looks like a Clojure function and acts like a Clojure function, but actually the macro is compiling the function body into something else. We compile it into a DAG. The DAG is abstract. It captures only the dependency flow of data through your functions without imposing any evaluation model. Throw away your typical call stack evaluation model. The rules here are different. You could imagine interpreting the DAG in many ways. We could use an async interpreter with promise-like chaining between steps. We could do an event propagation network with events streaming through the DAG one after another. In fact, such an event propagation network can be used to achieve reactive rendering like React.js, where functions are efficiently recomputed only when their dependencies changed. Let's tweak our vocabulary. Instead of saying reactive, let's say streaming. Since DAGs essentially give you streaming, they are natively asynchronous. And this is the key insight. If the computation is already streaming, inserting a small delay into the stream for WebSocket hop has no impedance with the streaming computation model. The composition of steps in the DAG is still well defined. So what happens when you actually run this Photon program? At compile time, Photon will color the AST, separate out the client and server parts. You now have two programs and they run concurrently. The purple program will run as far as it can. It doesn't get very far as it immediately needs a server result, so the program will park and await. It will not issue a request. It will not send a message to the server. There is no I/O at all. It will silently wait. The red server program is running concurrently. Its dependencies are all satisfied, so it is able to run the query immediately and then stream the result to the client. The client receives the result and unparks, continuing to render the view. You can conceptualize Photon as a reactive programming language. Unlike React.js, in Photon, the programming language itself is reactive. Reactive if, reactive for, reactive try-catch. Reactive DOM bindings are a special case of a more general reactive programming language. In Photon, the entire client-server system is expressed in the same unified programming language. Both front-end and back-end are reactive in streaming. And since they match, they compose just like we wanted them to in the problem statement. No more impedance mismatch. Let's be clear about the network traffic. The client sends nothing to the server. The client and server are like a sports team. They agree on the play in advance. The client knows where the ball is going to come, and the server throws the ball to where the client is going to be. The only network traffic is a single message. Here's a more interesting example with user input. Here is a DOM element. In React, input elements have a change callback. That is not the case here. This input function uses the return channel to return a stream of values bound to the symbol email, which is conceptually a stream. Note that email is in lexical scope of the server. How can lexical scope cross to the server? Recall that Photon functions are DAGs. When the input has a new value, the event will propagate and reflow the downstream DAG, sometimes crossing over a WebSocket. All right, here's a larger example. This is a CRUD grid component. If you're not a Clojure programmer, don't worry about it. The DAG is what matters, and we'll show you the DAG in a moment. The point is that there are red server queries inlined everywhere. There's even a for loop driving this table with row-specific queries inside the loop. This naive code is actually exactly what you would write if you were writing PHP and the database was co-located with your program. There is zero web framework boilerplate. No coordination of GraphQL queries, no client-side ORM or client-side cache. The network is not visible in your program. Here's the DAG. I want you to look here at this inner box. That's the for loop. The contents of the for loop are half purple and half red. It is both colors. Photon can see this same as you. Photon understands the underlying primitives that make up the for loop itself and slices the loop in half at a more primitive layer. And you can see that in this pseudocode. The for loop is in both places. The loop on the server is not blocked on any client dependencies. The server will enter the loop and run it as far as it can and then stream the intermediate environment to the client. The client will catch the ball and resume execution in mid-flight right in the middle of the loop. This is stunning. When we first saw this, it blew us away. Dear watcher, I want you to pause this video and think about this idea of slicing the DAG. Pause and convince yourself that this messy and tangled program, when presented as a DAG, is actually clean and organized. There are clear red and purple regions. There's a clean cut between them. And there is always such a cut for any real-world program, no matter how big and complicated, even in the presence of loops. Ready? Pause the video now. Okay, you're back. Let's talk about security for a second because this sounds really insecure, right? Actually, it is secure. Look at this green line. This is the security boundary. All the red logic is running on your trusted backend. Put your permission checks here. So the security model is equivalent to the backend for frontend pattern. If it helps, you can mentally rotate this model into the shape of a REST API, which has a security model you're accustomed to. To get REST, all you need to do is slow down the streaming by waiting for all the queries to finish before sending a big bash response all at once. The main question at this point is how far can the DAG abstraction scale? Can it do lambda, higher order functions, and closures? Yes. DAGs nest, you can embed a DAG inside a DAG. Look here where we call this field function with the two red parameters. Here's the function body. The red parameters are not used by the client, they stay on the server, and that is clear from the static information available in the program. When you define a Photon function, you're defining a DAG, and when you compose Photon functions, you're composing DAGs. Next is closures. Here's a closure. Quickly, the big idea here is that closures are higher order DAGs. DAG is a value. Closures essentially pack up a DAG, pass it around as a parameter, and then splice it. The operation I just called splice is the monadic join operation. This computational model is called self-adjusting computation, and Jane Street has a helpful article explaining this. All right, let's quickly recap what we've seen. Compiler managed network, this is so important. The compiler will produce better netcode than you could ever achieve by hand, regardless of the composition depth or how dynamic your application is. You know how every SaaS tool lags these days? Framing it as a compiler optimization problem is how you solve that. Backend for frontend pattern, gone. GraphQL, gone. Your whole web framework is gone. Think about how we even conceptualize web development work. Front-end team, front-end language, back-end language, front-end framework, back-end framework. We baked the platform into our org chart and then we shipped the org chart. Today's orgs cannot even conceptualize that it could be different. We're hosted by ClojureScript. By hosted, we mean a language embedded in a language. Photon is just a Clojure library. When you adopt Photon, you're not adopting some baby programming language with only 10 users. Clojure is battle-hardened, has an incredible community, and is commercially supported. Why else Clojure? Metaprogramming is roughly equivalent to monads, and its applications are underexplored. Most importantly, Clojure itself is hosted by JavaScript JVM. All your legacy code, we reach it. Want to use shell scripts as your backend? No problem. Project maturity, we have a pilot with a Series B startup, which is driving us through all the real-world edge cases like loading state, security, pagination, messed up business rules, etc. All right, why did we even do this? We didn't set out to build this. We set out to build a holy grail low-code application platform that scales to complex and messy real-world requirements. We ended up here because it turns out that this is the minimum level of ambition that is useful. So the question is really, what is the holy grail low-code tool that composable network makes possible? Well, do we have a killer demo for you? But we're out of time, so to see the demo, follow me on Twitter here. From Twitter, you can get to the demo. Want to be a part of this? Follow us, DM us, post type tweets, make introductions. Help us bring this to the world. I'm Dustin Getz, and we are Hyperfiddle.